So good afternoon, everyone. I'm Ummul Farah, a graduate student at West Virginia University, and I'm also part of the WVU Pollution Prevention team. As a team, we work with local industries to help identify ways they can improve energy efficiency and reduce waste, both to save money and operate more sustainably. Today, I'm going to be discussing an assessment that we performed for a small business in West Virginia. The name of the facility is GS Millwork, a wood products facility. The case study is called, we named is self-sufficient energy at a wood products facility. So let's get started. So first, I would like to give you background information about the facility. GS Millwork is a small business in Parsons, West Virginia. They produce custom wood trim, molding, and drawer boxes in the facility, which spans multiple buildings, as you can see in the aerial photo, totaling about 100,000 square feet. The building to the left is the office area. The remaining buildings are used for production. The facility runs on both electric and natural gas. Natural gas is used for heating the facility, while all equipments and the processes run on electricity. So our team was contacted to perform a general assessment for the facility, but they had one specific challenge they were hoping we could assist them with. The facility generates a lot of sawdust, approximately 10 tons per day. The facility is equipped with a vacuum system with intakes and equipped on each piece of equipment that generates sawdust. The system gathers and loads the sawdust into a trailer. Once the trailer is filled, the other trailer is moved into place to collect sawdust, and the filled trailer is hauled to another local businesses, which is approximately 2 miles away, where they use the sawdust for their industrial processes. Right now, the method is working sufficiently for them. They get rid of their waste at minimal cost. However, there are several concerns. First, they have no room for long-term storage of sawdust. The area highlighted on the aerial is the area they have dedicated to management of sawdust. This system is reliant on them being able to get rid of sawdust in timely manner. If there is a failure in this system, they would have to stop production until a solution is found. This leaves them reliant on the relationship with this other company, a completely separate business, to be able to continue production, which isn't a position a business wants to be in, if it can be avoided. So they hope to optimize and increase production moving forward, which would increase energy use and sawdust generation. So this is our proposed solution. So the proposed solution is to implement a combined heat and power, in short, CHP biomass boiler system at the facility. A CHP biomass system utilizes biomass to generate electricity and usable heat. So the biomass here is the sawdust which they are producing in this case. So in this case, the energy in the sawdust can be used to generate electricity to power the equipment in the facility, and the waste heat from the process can be recovered to provide heating for the facility. The CHP system has the potential to power and heat the facility using only the sawdust that has been a waste product for them. So how biomass CHP system works? So a CHP is a fairly complex system with several subsystems and many components. But there are three main subsystems. First, a boiler, then a prime mover and generator, and a waste heat recovery system. First is a boiler system. In this case, the boiler system, which is a fixed bed stroker boiler, will be continuously fed with sawdust from the facility. The heat generated from burning the sawdust will change water into high pressure steam. Next we have is the prime mover and generator. The steam generated by the boiler drives the prime mover, in this case a steam turbine. The turbine is attached to a generator which converts the mechanical energy from the steam turbine into electricity, which can be used to provide power to the facility. The final part of the CHP is the waste heat recovery system. A significant amount of the energy in the previous step will be lost as heat. That heat can either be recovered and used to heat the facility or exhausted out of the facility when heating is not needed. So let's see how the solution may work out for them. Sorry. So let's see how this solution may work out for them. First, let's look at the energy needs and cost of the facility. We obtained utility bills for a 1-year period from the facility and found the following information. Over a 1-year period, the facility used about 520,000 kilowatt hour. The month with the highest use was January 2023. Since the facility only operates Monday to Friday, this electricity use was across 21 days in the month, or an average of 2,327 kilowatt hour per day. So in other words, we can say that we need at least 2,327 kilowatt hour of electricity each day to power the facility. The facility also uses natural gases for heating, with highest use in the coldest months and the use also tapering off into the warmer summer months. The heating was left on over the weekends when the facility was not producing, meaning an average of 16.2 thousand cubic foot was used each day over the month with peak use. So as far as the energy costs go, the facility spent about $78,000 on electricity over the year and almost $26,000 per year for natural gas. So this is the energy use summary. Here we can see the annual energy use and annual energy cost and peak daily use. So moving forward, we will mostly discuss these values in MMBTU or millions of BTU. So what is BTU? BTU or British Thermal Unit is an amount of energy that it takes to raise 1 pound of water by 1 degree Fahrenheit and allows easy conversion and comparison between energy sources. So after converting, we find that the amount of natural gas and electricity they used over the year is equivalent to 4,216 MMBTU. To satisfy the needs of the estimated peak daily use, 7.9 MMBTU of electricity and 16.8 MMBTU of natural gas is needed. The next step was to see if we can satisfy those requirements with the amount of sawdust produced by the facility. This slide shows how energy is transferring from sawdust to electricity, and that is used as electricity and for heating. So let's look at a single pound of sawdust. A pound of sawdust has about 8,500 BTU per pound. So along the way through the system, there are going to be various losses that occur. When the sawdust is fed into the boiler, so the first step is when the sawdust is fed into the boiler, it is burned, which heats water and turns into steam. The boiler efficiency varies, but it's typically 85%. So about 15% of the energy, or 1,275 BTU, is going to be lost during this step. So this is the loss here. And the remaining 7,225 BTU that converted into steam energy is used to turn the turbine here, and which is used to turn a turbine that generates electricity. This subsystem is not incredibly efficient, only converting about 30% of the energy, and 30% of the energy. So the energy would be 2,168 BTU. Of the remaining 70%, which is 5,058 BTU, and about 10% losses that occur for mechanical, thermodynamic, and other issues, which is like 506 BTU occurs loss here for the mechanical issues, and we have rest like 70%, which is 4,552 BTU, which we can be recovered and used. Depending on the design of the system, up to about 80% of the recovered heat, like here is 3,641 BTU can be effectively used, while 20% of it, like 910 BTU, will be lost. So in summary, here is the summary, like how much we're going to, how much 1 pound of sawdust produces electricity, heat, and how much there is losses. So, and the overall CHP efficiency is 68.3%. So now we can figure out like how much sawdust it will take to meet their needs. If more than 10 tons of sawdust is needed to meet their needs, they would still need to use some electricity from the grid, some natural gas to provide heat, or both. If less than 10 tons of sawdust is needed to meet their needs, they should be about to fully power and heat the facility using sawdust instead. Ideally, we want these numbers to be close, enough sawdust to power the facility, but not too much left. Sorry. Not too much to left there so that they have to manage their extra sawdust as a waste. So based on the peak daily uses over the period, it would take approximately 1.8 tons of sawdust to generate 2,327 kilowatt hour of electricity. Similarly, it would take 2.31 tons of sawdust to replace the 16.2 MCF of natural gas. Since the 2.31 tons of sawdust will generate both 16.8 MMBTU in heat and a little over 10 MMBTU or 2,900 kilowatt hour of electricity, that 2.31 tons of sawdust will be able to meet both the electricity and heating needs of the facility. Now let's briefly look at the economics of upgrade. We estimate the implementation cost to be approximately $400,000. That's a lot of money, but since it will save them 100,000 or more in a year, the payback period is only about 4 years. So as far as environmental consideration of the upgrade, it's somewhat of a mixed bag. Essentially, eliminating their need for natural gas results in an annual reduction of 134 metric ton carbon dioxide equivalent. Based on the e-grid subregion, the electricity that is no longer being used from the grid accounts for a reduction of an additional 458 metric ton carbon dioxide equivalent, for a total annual reduction of 592 metric ton carbon dioxide equivalent. However, the facility must take care in design of the system to control emissions, including scrubbers and other emission control devices. If proper care is not taken in the design, the emissions could be significant. Additionally, the boiler will cause an increase in water consumption. So, however, based on our calculation, they will only need about 2.3 tons of the 10 tons of sawdust generated each day to fully heat and power the facility. There are options that can be considered. The sawdust could be pelleted and sold by the facility for a profit as an additional product line, donated to charity for local use in an area where wood heating is not uncommon, or sold in bulk to other facilities that heat using biomass but do not have a consistent source. The CHP could be sized to use 10 tons of sawdust or more per day to eliminate the need for disposal, with some additional capacity for increased production. With some thoughts and consideration, it is likely that a manageable solution can be found. So, in summary, a CHP system would make this facility more self-sufficient while reducing costs and benefiting the environment, but it might not completely solve their problem. But we'd still consider it as a win, though. Thank you. That wraps up our case study on GS Millworks self-sufficient energy. Thank you for your time and attention. Please scan the QR code to share your quick feedback. And I'd be happy to answer any questions you may have.